Let's see. So this is, you read in your in the textbook about a Vandergrift generator. This is a handheld portable Vandergrift generator. And this one is nice. This one has this is the same mechanism, but they made it, the first version they made with so you can't see the mechanism. So the second version has the mechanism, so you can see it, which is kind of neat. So there's a switch here, and it's a little hard to tell, but when you turn it on here, you can see the belt spinning here. It's turning, and there's you can hear it. There's right here on the end here, there's something a little needle that's touching the belt, and it collects charge, scrapes frictions. So it's a triple electric effect, stripping charge off, and then you can hear the charge. You hear that? So it's starting to charge up. I have 2 of them, so we can have 4 times the fun, right? So this is a piece of Mylar. Mylar is a good conductor, so there are different materials, insulating and conducting. The difference is for an insulator is where you put the charges, that's where they stay. Whereas a conductor will allow the charges to move around on the substance, on the body. And what motivates, what determines where they move is something we're not really prepared to do yet, to consider yet, but obviously they're going to move in response to forces that are present on them. And so we're not quite at the point where we can determine exactly what happens. But this is a Mylar sheet, and I'm going to charge it. And because the charges are all of the same kind, they're going to repel each other. And so the Mylar, being flexible, will change its shape. Okay, I'll let Mr. Miller keep this one going. Oh, I got to start over again. It lost its charge. There we go. Sometimes the wand needs to be recharged. There you go. Don't touch it. So this is there's some other one in here, which is pretty neat. Okay, this is also Mylar, a little bit different shape. Yeah, pass it around.
Where's the button?
There you go. Don't let it hit the ceiling because it'll stay. Well, it's not too bad in here. In the lecture hall, I did it one time, and we had to wait for it to fall down. It's too hard to do. That's awesome. Pass it along. Oh, it discharged. Oh. Okay, so you see, so there's 2 things going on in the Mylar. Obviously, the forces are causing the Mylar to change shape, but then the forces are rearranging the charges, or the forces among the charges on the Mylar, causing the Mylar to change shape. So obviously, there are forces present. But what you can't see is that the Mylar also distributes the charge easily, and that's because you only have to touch one part of the Mylar for the charge to spread out all over the Mylar. So I only touched one part to charge it, and then the charge is redistributing, moving freely, and that has to happen in order for that to do what it's doing. So. There's a part missing in this. This kit has in it a little light bulb. I think it's a neon light bulb, and you can get it to light just by moving the wand close to it. Unfortunately, it's missing. I don't know where it is. That was the demo I was looking for. Oh. Okay. And the good news is also, yeah, those Mylar things, of course, are very delicate, so be careful not to break them. Okay, well, so wake up, come back. We also have, it's kind of nice now, the podium has been restored, but oops, where did it go? Hello. It went to sleep. I gotta somehow turn off the setting on this thing. Here we go. Okay. you know, just pops open like that. The charge moves around very quickly on the conductor. All right. Thanks. Did you hear that pop? Yeah.
The charge left.
Okay, so let's see. I'm going to. I don't know that I need to change this any. Zoom in a little bit. I'm going to turn off this light here. Okay, so I'm going to pass out the solutions. Now we're going to go over them briefly here in class. And then you can correct your homework as we're going over it here, and then turn it in at the end of class. I have another solution for you, but it doesn't have a staple in it. I'm off by one for some reason. Okay, so what we're trying to learn is how to deal mathematically with vector fields and scalar fields. And so this implies one thing that's really nice to be able to do is to do contour plots. Excuse me. Contour plots of functions, and so we're going to look at that briefly. Being able to do integrals and derivatives, partial derivatives and gradients. And it looks like most people generally have it down, so, but let's go over some of these. Let's see. Excuse me here a second while I get organized. Okay, so let's go over the worksheet for calculus first. The third problem there was to go over these, being able to do the derivatives and the antiderivatives, and which is also known as the indefinite integrals. So you should know these integrals. We'll be using them along with a couple of other derivatives that we'll need. So I expect you to have these memorized. There'll be some slightly more complicated integrals that we'll be doing that I may give you a table of integrals on a test, or you should, if you don't have a table of integrals, you should get one. They're certainly available online now. I paid, I think it was like $5 for this, back when I was a student, for this volume of integrals. It was like that thick, written by a couple of Russians, and it was terrific. It was the best $5 I ever spent, and it's just loaded with stuff in there. Now I can just bring up Mathematica and type in it in. But I check Mathematica against this big volume. Okay, so then so these based on doing these things as evaluating the indefinite integral at certain endpoints, or known as definite integrals. And any questions about these definite integrals? So the co-requisite for this class is integral calculus. So I'm not assuming that you've already had this, but most of you seem to be comfortable with it. And so I'm not going to spend any more time on it and if there are any other questions, please certainly contact me by email, come by, we'll talk about it. Office hours now I've set up, at least for the time being, same as they were last term, Tuesday and Friday from 2 to 3:30. And of course by appointment, by email, any other, we'll work out another time. And I'm going to send out a survey again, because I know your schedules may have changed some, to try to optimize the office hours. But for now, they're the same as last term. Okay, so there are no questions about that. I know there might be some questions about this. The definition of the integral is the area under a curve. And he goes through in the text this argument where he proves the fundamental theorem of calculus, which is that the definite integral of the derivative is equal to the difference in the function at the endpoints. But you can do the same thing, same sort of procedure, and that is, and if you think about it, what we're doing here let's see. That's not. Here we go. Okay, that's what I needed to do. I'm having to remember this. In this particular case, we're evaluating the area under the function x. So f of x is just x. And we're going from 0 to some limit x. And we're going to divide this up into rectangles, and we're going to calculate the area under that curve. And of course, you should see that this is half of a square. This is just a square has two sides of x. So the area here under this should be 1/2 x squared, half the area of the square. And so we divide this interval from 0 to x up into little pieces, and the width of each piece is the side of the square divided by the number of pieces that we're going to divide it into. And so the values of x go 0, delta x, 2 delta x, 3 delta x, 4 delta x, and so forth, all the way up to n delta x, which is, of course, just x. Okay, so that's the values of these x's along this point here. So that gives you, and then the width of each rectangle is delta x. And then, of course, now we could draw a rectangle here. And so the height of each rectangle, of course, is also the value of x itself, which is given here as 0, delta x, 2 delta x, and so forth. Okay, so we're going to sum up the values of x sub n times delta x, right? The height is x sub n, and the width is delta x, where x sub n is just n delta x. That's the nth value of x. And we're going to sum it up. We're going to sum n of these up. Okay, and so x sub n is then n delta x, and delta x is then common term to all terms in the sum, so we can pull the delta x out, factor it out, and we're just summing n, little n, from 1 to big N. Okay, and then I go through proof in the homework. Let's go look at that. Minimize that. Oh, minimize the wrong thing. Oh, I got it. I'm still remembering how to use this. Nuts. Stop. Whatever you're doing, stop. I just had that up. There. No, it's not responding. Adobe Acrobat Reader DC not responding. That's what's going on. Something is. I had it here. So let's close this. Not gonna let me close it either. Okay, technical difficulties here, but let's go through this. You can demonstrate that the sum of integers up to a maximum value is that maximum value times its neighboring number, the next highest number divided by 2. And I go through in the homework there to demonstrate that this is true. You can just try a few of them and see if it works. That's one way to kind of convince yourself that it works. But then a more stringent way, of course, is to do it by induction. Let's call this S sub n. First, you prove it for n equals 1, and that's easy because you're just adding 1 to 1. God bless. And you can see that S sub 1 is equal to 1 here, as given by that, and that's what it should be. Then you can assume it true. Assume that S sub n is in fact 1/2 n plus 1. And then prove that the next one is in fact given by incrementing n by itself by 1. So prove that. And I showed how to do that in the homework, so I won't go through this. Okay, so then we're given that n equals 1. The sum of all the integers up to a maximum value is in fact this, for any value of big N. And so now we go back to, we look at the integral of x dx from 0 to x defined as a sum. Then we remember we had a delta x squared term, 1/2 n plus 1. And going back to the definition of delta x, it's x divided by n. Okay, so this is 1/2 x squared, and now we divide the n squared in the denominator there into the n times n plus 1, so that gives us 1 plus 1 over n. And now we take the limit, this is all in the limit, as n goes to infinity, this limit now, you can see the 1 over n term goes arbitrarily small, and so now the integral of x dx from 0 to x is 1/2 x squared. So and that was the result we could see we needed to get. But you can see the power of the integral now. The next problem is doing the same thing for a parabola. Now you're going to calculate the area under this parabola. It's not so clear from looking at that what it should be. You could go through a geometrical argument to find out that this should be, 1/3 x cubed. But the calculus makes it easy to do, just learning how to do the antiderivatives. Okay, questions about that? The purpose of this last two problems was to demonstrate the nature of the integral, of the definite integral, as an area under a curve. It's clearly related to the antiderivative, but it might not be obvious to you. In fact, it shouldn't be obvious the first time you go through this. That the definite integral, in terms of the antiderivative, evaluating the antiderivative at two limits, actually gives you the area under the curve. That shouldn't be obvious to you, I don't think. So this exercise here is to help you to see that that's going to be the case. Okay, so now the next one, worksheet that I want to look at, is going to be, let's see, what was it? Partial derivatives was the next one. God bless. Partial derivatives, I think, was the next one. Let's see if I can bring it up. Ah, I forgot. Turn it to a pointer. See if it's going to come up. Why is it not opening that document? It seems that for some reason Adobe has gone to sleep and I can't turn it off and try to turn it back on. Okay, so let's go back over the partial derivatives here. We did that a little bit in class, so maybe I don't need to go through it a lot. But one that we will use frequently, a partial derivative, would be something like this: partial derivative of 1 over the square root of x squared plus y squared. So now it's a combination of the chain rule and recognizing that y is treated as a constant for this. So this is minus 1/2, and then we have x squared plus y squared to the 3/2. And then you take the derivative of x squared plus y squared with respect to x, of course, and that the y squared is a constant, so that derivative is 0. So this gives you a 2x, and so altogether this is x over x squared plus y squared to the 3/2. This particular form here, 1 over the distance, is something we'll see a lot of in electrostatics. And so taking the partial derivative of that, and also the partial derivative of 1 over, in 3 dimensions, square root of that, okay, is then okay. And so then when we're forming the gradient of a function, remember, is a combination of the partial derivatives, but don't forget the direction vectors here. You have to have the directions in it. Don't forget these unit vectors. That's a common mistake, is to drop the unit vectors. Remember, this is a gradient. the gradient, I'm sorry, this is a vector. The gradient is a vector. It has a direction, not just a number. Okay, so let's look at the gradient of 1 over the distance. 1 over the distance. And remember, the distance is the square root of the sum of squares of the Cartesian components. This is now getting us into the gradient worksheet, jumping ahead a little bit. But you can see now from what we just did that this is going to be x, it's going to be a negative sign out front, x hat plus y hat plus z hat, divided by x squared plus y squared plus z squared to the 3 halves. And that is something we're going to use all terms. We're going to keep coming back to this. And in fact, suppose f is a function of distance, some function of distance, where r is equal to the square root of the sum of squares. Then let's evaluate what the gradient of that function of distance alone. So first we're going to use the chain rule here. So we have x df dx, right? But f is a function of r, which is a function of x, y, and z. And so you can see this is an example where we're going to use chain rule a lot. So when we take this partial derivative here with respect to x, we're first going to take the derivative of f of r, and then we're going to take the partial derivative of r with respect to x. So for each one of these, we have an f prime of r. Oops, d r dz. And we just did the derivative of 1 over r, so it's get a similar result for derivative of r. And so the gradient is of a function like that is pretty easy to evaluate. We're going to have a f prime of r coming out, and then we have the gradient of r. And the gradient of r is x times dr dx plus y hat dr dy plus z hat dr dz, and the partial of r with respect to x, doing something very similar to what we did before, is going to be x over r. And the partial derivative of r with respect to y is y over r, and the partial derivative of r with respect to z is z over r. So here's a nice result that we're going to be using a lot. If f is a function only of the distance, then the gradient is going to be x hat plus y hat plus z hat over r times the derivative f prime of r, whatever that is. And what is this thing here on the right here? So if we remember that r vector is x hat plus y hat plus z hat, and r is the magnitude of r, then what is r over its magnitude?
Unit vector.
It's the unit vector in the radial direction, pointing outward. So in other words, this result can be expressed simply as the derivative of f pointing in the direction pointing outward. That makes sense. If you remember, f is only a function of the distance. Okay. Now another thing that we need to do here in these, let's go over the contour and the gradient, going back a little bit in the gradient homework. Let's consider there was a function I gave you, f of x is equal to the absolute value of x. But I'm considering this as a function of 2 variables, so I should rewrite this here, excuse me, as f of x and y. But it doesn't depend in its value upon y. Okay, so now let's sketch that function. There are multiple ways, different ways of sketching that function. One way is to try to make a 3-dimensional plot of it, which is difficult to do, but it's doable. If let's suppose we make this y and this x, and then this is the function like that. So this function is going to look like a wedge here, aligned along the y-axis. And as I said, it's difficult for me to draw these sorts of things, but it's a wedge. Let me use my hands. It's like this. An easier way to plot these is with contours. So a contour plot is to take a cross-section of a wedge, or any function, and cut it at constant altitude. So if I have this wedge like this, for example, and I'm going to make a cut across it, I want to know where on the xy plane that the function has value, say, 1. Okay, so, well, we can look at that. Where does x, the absolute value of x equals to 1? Well, that's, of course, where x equals 1 or x equals minus 1. What do those look like on the xy plane? Those are parallel lines, 2 parallel lines. So a contour plot would be to take f equals 1 and plot where on the plane that the function equals those values. So those are parallel lines for this function. And where f equals 2 now, or where x is plus and minus 2, x equals 3, and of course f equals 3, and of course f equals 0 is right there. And you could label these contours with the value of the function. That might be helpful because then you can tell it's what it's about. Otherwise, a bunch of parallel lines, it's kind of hard to know what's going on. So it's often helpful to label these with the values of the function. Okay, now let's take the gradient of this function, the gradient of the absolute value of x. Okay, the absolute value of x depends, of course, on whether x is positive or negative. If x is positive, then the absolute value of x is equal to x. If x is negative, the absolute value of x is negative x. So the derivative of absolute value of x with respect to x is either plus or minus 1. So we could write that the partial derivative of the absolute value is the secant of x is plus or minus 1. Depending on whether x is positive or negative, and the partial with respect to y, well, it's 0 because, the partial derivative of the absolute value of x with respect to y is 0, of course, because x does not depend on y. Okay, so contour plots then are an easier way to do some of these. The next function, I think, was x squared plus y squared over 2, and you can see it's a function simply of the distance. It's 1/2 of the square of the distance. So let's draw the contours of that function. The function, of course, is a bowl. A bowl with circular symmetry. So if I cut a bowl at some altitude from the bottom, then I'm going to get concentric circles for the contours. And the lowest contour is here right at the origin, and I get another one. Now, what is the spacing between the contours? That's the question when you're drawing contour plots, is to get the spacing correct. The space between the contours tells you how quickly the function is changing. If the spacing is even, like in this example that we did just here a minute ago, the spacing is even, that means the slope of the function is the same everywhere. But the slope of the function here is increasing. So that means the contours are getting closer together. As you get farther from the center of the bowl, now where I cut it off, the next time I cut it off at twice that height, but now it comes faster. So this contour spacing is diminishing as I go farther out for this function, because the slope of the function is increasing. And so my contour should reflect that if you're sketching the contours. Closer contours means a steeper slope. On a topo map, if you're familiar with that, when you go hiking, you take a topo map so you can see the altitude changes on the trail. The closer spacing on the contours means you're going to be moving uphill or downhill fast. Whereas if the contour spacing is big, it means you're out on a flat open space or a flat space. You're not going to have to work as hard going up and down. Okay, so the contours of this function look like that. I'm sketching them, of course. I have more precise plots in the solution that I handed out. How about the gradient? Now the gradients, just by looking at this, you can tell the gradients. The gradients are perpendicular to the contours. And so the gradient is going to be pointing outward, like that. And we'll see if that comes out. And in fact, as you get farther out, the increase in length, because the magnitude of the derivative is increasing, So these are getting bigger out here. And what is the length of the, what about the vector, the gradient right at the origin? Well, it's 0, because you're at a minimum of the function. So let's evaluate that then. The gradient of f, just by applying the partial derivatives here, gives x hat plus y hat, which is just the position vector. So the for this particular function, the function is increasing in magnitude with the distance, linearly with the distance from. So the magnitude of the gradient is r, is the distance, and the direction of the gradient is r hat. So I could summarize this particular function as having a gradient, has a direction pointed outward, and its magnitude just proportional to the distance. And in fact, that fits in with what we just did. Here we see that f is a function of the distance is just r squared, 1/2, right? So the gradient of f, what we wrote before, is f prime of r times r hat, and f prime of r is just r, so this is r hat. Okay. For that particular function. We're going to do a lot of functions that have simple dependence on distance from the origin. Okay, how about that third one is a little harder to do because it's three-dimensional. What was the function? I can't remember exactly here. Was it
1 over the square root of.
Okay, there's that promised function. There it is. Right. We're going to do this a lot, so that's why I pulled that one out. What do the contours of this look like? Well, it's a function in 3 dimensions. So the surfaces of and it's a function only of the distance from the origin, and of all the points at a fixed distance from the origin are on a sphere. So the contours are going to be concentric spheres, centered on the origin, all of them. What about the spacing between the contours?
You shrink it shorter the further out it is.
I think so. So let's see. Farther out it gets, the function is changing less. So the spacing of the contours as you get farther out is increasing in contrast to the previous one we did. So if I take in other words, the spheres are getting farther apart from each other. As I go from f equals 1 to f equals 2 to f equals 3, the radii are increasing. The spacing of the spheres, yes, sir.
So if it's a function of 3 variables, wouldn't there be like a 4th dimension, I guess, or a 4th?
It would be very hard to draw what we were doing before, right? When we have the function of 2 variables, we can plot the third coordinate as being the value of the function. Difficult to do this, so I guess that 4th one is like, here's the sphere, here's the next sphere, here's the next sphere, here's the next sphere. Or I could have a motion picture in time, use time as the 4th, the value of the function. It's harder to do. But what you could do in this case is to take a cross-section in the xy plane, set z equal to 0, and take a cross-section of the function, and then you can see what that would look like. And so I can plot that, and so these contours now are going to be getting really getting close together as I get close to the origin, and then spreading out. Farther out I get, as compared to the one I was doing before. And in fact, the function diverges. It's undefined at the origin, meaning its value becomes unlimited. There's no limit to the value of the function as we get close to the origin. And so the gradient of this function is going to be, you have to go through what we just did, and this would be all over to the 3/2 with a negative here, right? Which is also equal to r over r cubed. The vector r divided by the cube of the distance. Which could also be written as r hat over r squared. And we can see that again if we recognize that f is 1 over r, then the gradient of that f, of course, remember, is f prime times r hat and f prime of r is minus 1 over r squared r hat, and there should be a negative sign up here, by the way. Okay. Negative 1 over r squared r hat. Okay, so we'll be doing a lot more of these functions that depend only on distance in some simple way, and so the gradients of those will be, you need to be able to do them, and so that's what we're going to be looking at. Okay, so now finally then I think they'll, are there any questions about the gradients, partial derivatives? Okay. Just a second here. Okay, so the last thing then was the hold on just a second here. Okay, so the last sheet was on forces and potential energy. So as we talked about last time, if we have then a potential energy which depends on x, y, and z, the force associated with that is the negative gradient of the potential energy. So the force points in the direction in which the potential energy goes downhill the fastest. That's what this tells you. Remember, the gradient, the direction of the gradient is which way is uphill, and its magnitude is the slope in that direction. So it's a negative sign, so it's an opposite to that. It's the negative. It's which way is fastest, which way do I go that reduces the potential energy the fastest. That gives you where the force is directed for a conservative force. And also then the potential energy between, the difference in potential energies between two different points. Let's see. Is given by calculating the work done. This is in one dimension. Okay, so you should be able to apply the gradient. Remember, the gradient's a vector. Got to make sure you get the directions involved. And this integral, of course, depends on how f depends on the distance. So the gravitational potential, for example, if we find that the force law for universal gravity can be written this way, which means that it's directed inward, so the direction is negative r hat, which means it's directed inward, and it diminishes like 1 over the square of the distance from the origin. Okay, so you should be able to demonstrate then that that's related to a potential energy, which goes like 1 over the distance. And in getting this, we're setting the potential energy at infinity to be 0. We're choosing, in that case, our reference point to be where the force goes arbitrarily small. Farther and farther away, I can set any sort of value of the force you like. I can always go farther away and the force will be smaller than that value, so I can... Okay, that is my point of reference. Okay? All right, that sets the stage now for us to do these basic things that we have developed mathematically, sets the stage for us now to go on. Chapter 2 develops a lot of this, but we'll use these basic things to continue to build up. Okay, so we have a few more minutes left, and I want to go over the, get you prepared for next homework. So please, on your way out, stack up your homework on the way out. I want to prepare you now for the second homework, which is due on Friday. The first thing is, the first work part there is some more exercise on sketching vector fields. So you've done something like that. We just did this. This is a vector field. And so you've done some sketches of fields. Oh, I guess I should, going back to that, looking back at the at this one here. Of course, the gradients here now. What are the gradients going to be looking like? This is where the function goes like 1 over the distance. Well, always perpendicular to the contours. In this case, the gradient is diminishing as you get farther out, so the arrows here are going to be shorter, pointing, oops, I'm sorry, excuse me, they should be pointing inward, because the gradient, the function is increasing as you get closer to the origin, so they should be small arrows here, and then bigger arrows here. Now you can see we're getting into a problem here, because it's going to be harder to show that. This function starts getting so big near the origin, it starts getting hard to draw. So you can do is kind of a sketch like that, I think. Okay, so that's a vector field, and you're going to do some more exercises on plotting vector fields that are not necessarily gradients. That is, these will be vector fields which are not themselves necessarily gradients of something. So, for example, this one is easy. That's one we've just done. But how about a y x hat minus x y hat? It's not associated with a contour. You're not going to draw contours first for all these functions. You're going to sketch vector fields that may not be associated with as a gradient of a function. So you don't start off with contours in this case. So the way to plot something like that is to take sample points. I'm going to take points on this plane, and then figure out what the arrow does at different points, and just draw a few, and then you'll get the feel for what it looks like. Okay, so this one, along the x-axis, y is equal to 0. And so it's pointing in the negative. If x is positive, it's pointing in the negative y hat direction, and it keeps increasing the farther out you get. So the arrows look like this. Should be doing this in a different color, like red, make it a little bit easier to see. Okay, do you see why it does that along the x-axis, like this? Okay, so you picked some points along the x-axis. Let's pick some points along the y-axis. When x equals to 0, this function is pointing in the positive x hat, positive x direction, and it's increasing as y increases. Okay, now really you shouldn't stop there. You should pick some points off of the axes. But this particular function is simple that it's enough. But you should really pick some other points. This function is so simple that you've done enough. Now there is no function whose gradient is this, right? So there are no contours to draw in this function. But that's a vector field, and it's an example of a kind of a flow, right? You could think of something spinning, maybe water flowing around in a bowl, something like that. Okay, so you're going to plot some vector fields, not necessarily functions that are gradients. Okay, and that's the first one you're going to do. Okay, and then we're going to finally get to looking at electric fields and understanding Coulomb's law. Okay, whoa, Coulomb's law. Coulomb's law is a way of, it's a force law. Again, remember, we're concentrating on fields and the forces that they produce in this term. So the force law for a charge, two charges, one of which is placed at the origin and can't move. Don't move, don't let them go anywhere. Now that generates a field in the plana surrounding it. That's my 5-minute warning. That generates a field in the plana surrounding it. And such that, and that field propagates outward, and that field is in the plana is such, the plana is such now, it's conditioned as such, so that if there's a second charge out here that the plana is in contact with, that will now produce a force on that second charge. And again, both of these charges have to be stuck in place. You can't let them move, but I can measure the forces on them then. And the magnitude of this force, the force on 2 caused by 1, is going to be equal and opposite to the force on 1 caused by 2, because the second charge also changes the plana around it, and that propagates outward. Okay, and so the force law then, the force on 1 by 2 is going to be the opposite of 2 by 1. So Newton's third law is preserved by what these are called electrostatic forces. And by electrostatic means I put the charges in place and don't let them move, and I wait long enough so that all the fields have settled out, and which is very fast, right? Because the fields propagate at the speed of light, so I don't have to take long if I'm doing it on the table here. Okay, so just make sure the charges don't move around. Okay, so the electrostatic forces satisfy Newton's third law. Okay, and also that can be written then as in terms of the product of the measures of the two charges, and we call the measure of charge of type 1, we call those positive, and of the other type, we call them negative. And then I can collapse all of these interactions in, because two positive charges repel, two negative charges repel, so I can write that as a product of the two charges, right? Positive times a positive is a positive, positive, negative times a negative is a positive, so they still have the same. I can collapse the force law into a very simple expression. And if they're opposite, if they're different types, positive and negative, it's attractive. Has exactly the same magnitude, but in opposite direction. Right, there we go. Okay, so it looks a lot like Newton's law of gravity. Inversely proportional to the square of the distance is proportional to the charges, the measures of the charges, right? And it has the direction vector R12, and let's go look at this R12 here. Here is, stop, that's not what I wanted. Here. Okay, here is the vector R1, 2. R1 comma 2 means the vector goes from 2 to 1. It's that vector. And this is determined here if I have, it doesn't matter where my origin is, I have some coordinate system here. Here's my origin for my coordinate system. This is R2, this is R1, the third leg of that triangle. And remember, this is the difference in 1 minus 2. Be careful you're not doing 2 minus 1, but it's 1 minus 2. It has the same distance, but opposite direction. Okay, and there's this K, which is a lot like the G in Newton's universal law of gravity. It's some constant. Now we starting units to get into the subject of units, and units are a complicated subject in electricity and magnetism because the units that were first developed were kind of made a lot of sense with what they were doing, but then later, especially in theoretical physics, we adopt a different system of units to make things simpler. We set K equal to 1, which alters the way we measure charge. So there's two different systems of unit. There's the SI and the CGS. And he writes the book, he puts in the book, especially in the early chapters, making it possible to do it both ways. So for the SI system, K is related to this, what's called a permittivity of vacuum, whereas in CGS, K is equal to 1. And so the measure of charge is different in these two different systems. The measure of current is different. A lot of fields, all the measures are different in these systems of unit. SI is what you will encounter if you take an engineering course, and if you're going to talk to engineers, you've got to talk SI because they don't know CGS for the most part. CGS is centimeter gram second. It's another kind of metric. They're both metric, based on metric, but the question is, how does one measure the charge? Okay, excuse me. Yes, thank you. Okay, so now I just want to write just a little bit more. I'm holding you just a little bit longer, and I know my recording is about to turn off here, but there it is. The electric field is determined by dividing the force by the charge. That's how one would measure the electric field. The electric field is present regardless of whether there is a test charge present or not. That second charge is there. There's a force on it, so I can determine the magnitude of the electric field, because the magnitude of the electric field and the direction of the electric field is determined by measured by looking at the force produced on that. But there's an electric field present whether there's a second charge there or not. The first charge produces the electric field in the plana. That is, it alters the plana